Okay, so let's come back now and talk about effusion. So effusion is a little bit different. You know, they may seem like the same thing, but the rate of effusion is a little bit different in this case. So it's pretty much the rate of fusion is the rate at which a gas diffuses through a tiny pinhole and into an evacuated chamber or a vacuum. So it's the rate at which it kind of goes through a partition. And I'll have a better example, a drawn example after this, after we talk about this image here. Okay. So the time required for the gas in the syringe to enter a tiny, like pinhole, the needle is a very tiny hole, to escape into an evacuated flask. So that rate is measured, or the time required to exit the syringe and into the flask is the rate of effusion. So the faster the gas molecules go through the pinhole, the less time it takes for the gas to escape into the flask. So the faster the gas is moved, the faster it will pass through the syringe and into the evacuated flask. Okay. So Graham found that the rate of fusion is inversely proportional to a molecule's density. So the lighter molecules will diffuse faster and effuse faster because they have a lower density, and so they have a lower molecular weight, more mass. So they're not as dense, so they can move more freely. So diffusion here, you're mixing when your things mix, and effusion is when gas particles escape through a narrow opening or a pinhole, and diffusion is where you have a kind of like a membrane where gas particles can go in and out, and that describes diffusion. So what this means is that since we can use the ideal gas solid state that equal volumes of different gases at the same temperature and pressure have the same number of particles, we say the number of moles per given volume is constant. So that now equates that the density can be we can kind of say, the rate at which molecules diffuse or effuse are going to be dependent on molar mass or molecular weight. So we can represent Graham's law like this. Rate of fusion is proportional to 1 over the square root of the molecular weight. Okay. So just for like diffusion, he found a similar relationship for effusion. It suggests that light particles, such as hydrogen molecules and helium atoms, move faster than heavy gas particles, just like the equation kind of suggests, right? Okay. So if we know if the rate of diffusion or effusion, if it's related to its average velocity of the gases, we can get this relationship as well. And you see here, it looks pretty much similar to what we've seen before for average speed in the previous example we did a few slides ago. Okay, so the relative velocities are inversely proportional to the ratio of the square root of the two gases' molecular masses or weights. Okay, so here's some data here to suggest this. The time required for, let's say, a sample of gas to escape through a very small hole into a vacuum, and we see here the time it takes for hydrogen is 5 seconds, and as we increase the mass ever so slightly here, going from 2 to 4 to 17, air is about 29, oxygen 32, 44, and then 64 for sulfur dioxide. And you see here the times, there's this increasing time relationship as the molar mass increases. Okay? And if we graph this graphically, we can see a direct relationship here. The lighter the gas, the faster it will move, and the less time it takes to diffuse. In this case, effuse through a small pinhole. Okay, there we go. All right, let's try this example here. Bromine vapor is roughly 5 times as dense as oxygen gas. Okay. Calculate the relative rates at which bromine gas and oxygen gas diffuse. Okay. So we if we rewrite the equation here, let's just say it doesn't have to. You don't have to. It doesn't matter what 1 and 2 is really. But what we should, it depends on how we set it up. Okay, so in this case, we know bromine is roughly 5 times as dense as oxygen gas. So what that means is that oxygen should be, this means the ratio of the molecular weights is going to be 5. So the rate in which the speed, the rate at which the speed should be the square root of 5. So let's just set that up right here. Rate 1. So let's call this of oxygen, O2. And then the rate of bromine, rate 2 will be for bromine. Okay? Okay. So we know they're inversely proportional to the molecular weights, so we should have molecular weight of bromine here, and then on the bottom we should have molecular weight of oxygen. Okay, so if we say it's roughly 5 times as dense, we should get an equation. So let's just back up here, make sure we wrote the equation right. Okay, so the rate of the speeds, right, should equal 5. Right? So this rate of speed should equal 5. Square root of 5, right? Because that's the relative density there. Okay? So if we plug into everything here, we can figure out the rates of diffusion. Okay? So if we do, if we just kind of show that it equals square root of 5 here, we could say, all right, square root of, so the molecular weight of bromine is about 160 grams. So we're not going to be exactly exact here, grams per mole. And then oxygen is about 32 grams per mole. Okay. So if we simplify that fraction here, we will see it's 160 divided by 32. That's 5, right? So that will equal square root of 5. So we know that's going to be true. Okay. So if we take the square root of 5, we will get 2.236. So we can say oxygen diffuses about 2 times faster than bromine. So that's how we would do that. That's how we do that problem. So we set the rates. We know the rate, right? So if the rate is equal to proportional to the densities, which in turn is proportional to the molecular weights of the gases, we can figure out, relatively speaking, how fast is oxygen compared to bromine. Okay, so if we did the opposite, we wanted to find the rate of bromine, it'll be square root of 1 over 5, and that'll be probably, let's see here, what's square root of 1/5? So 0.2, rate should be 1/2 hour. So yeah, that would be about 0.1. So it'll move 10 times slower. Well, I guess you wouldn't be able to really think about that, probably. Huh, okay. So it moves, I'm guessing it moves 0.1 times as fast or slower than bromine. And yeah, so it moves like 10 times slower as it diffuses. So it's not exactly the opposite, right? Um, so, but that is interesting actually. Let me see. So we did 32 divided by 160. Yeah, that's about 0.2. And we square root 0.2. Okay. Okay, it's about 0.447. So we divide that by 1 divided by 2.236. Yeah, so it's actually the reverse. Sorry, I guess I calculated it wrong. So yeah, so we can either say, yeah, it probably makes sense if you find out how much faster oxygen is than actually saying, okay, bromine is this time much slower. So it's much more, I think, natural to say, okay, this is like 2 times faster. Okay, so that's how we would do that problem. Okay, now let's calculate the molecular weight of an unknown gas. If it takes 60 seconds for 250 cubic centimeters of the gas to escape through a pinhole in a flask to a vacuum, and if it takes 84.9 seconds for the same volume of a gas of oxygen to escape under ideal conditions. So in this case, we're going to figure out the identity of the gas based on the molecular weight. So we can also do that. If we don't know the identity, we can calculate its molecular mass and determine what gas it is. Okay? So, what should we do here? Rate 1 over rate 2 equals the molecular masses here, MW2 over MW1. Okay. So, we see here that if we plug in the rates, okay, so let's plug in the rates. Here we have 250 centimeter cube per 60 seconds over 250 centimeters per 84.9 seconds. Okay. So remember, we can also represent. Okay, if it's in a flask, right, it's going to be a it's going to have some 3D character there. So that's why we list volumes, volume per second. So that's also another way to represent the rate, right? It's traveling up this cylinder or in this container, which is, it's not flat, right? It's not moving in a straight line. It's moving up, down, left, to right. So we can do volume divided by the time it takes to cover that distance for the rate. Okay, so we do that. We're going to now say, okay, it's going to be equal to the square root of our molar masses. So we know that oxygen is 32.00 grams per mole, and we're going to solve for M1. Molecular weight 1, right? Okay. So now if we simplify things here, we will get approximately 4.17 centimeters cubed per second over 2.94 centimeters cubed per second. Okay, so we squared that because we want to square these terms, right, to get rid of the square root. So if we do that, 32.00 grams per mole over molecular weight 1. We're going to square that too, right? So put a square here. So remember, square root is a nice way of saying, okay, x to the 1/2 power. Okay, so if we square this, so if we're going to square that, it's like doing this. So squaring this, and when we have exponents outside of each other, you can so if you're doing if you're squaring an exponent, what you can do is just simply you don't add them, you multiply them. So you multiply times, right? So this will be x to the 2 over 2, which is x to the first power. So that square root now will disappear. Okay, so if we do this, we will get 2.012 equals 32.0 grams per mole. Okay. Over molecular weight 1. So now if we solve for molecular weight 1, we will get molecular weight 1 equals 32.0 grams per mole divided by 2.012. Okay. And what we get is 15.9 grams per mole. Okay, I don't know what kind of gas that would be, but maybe that's not important. Does anything up here? No. Maybe it's methane. So methane is CH4, and that's pretty close to methane, I would think. It might be CH4, because carbon's 12 plus 4 equals 16. So that's pretty close to 16, so maybe it's that, but we can also be a little bit off because of our rounding here. So it's probably methane. So it's probably CH4. Okay. So if we didn't round, we would get, let's see here. So 250 divided by 60 divided by 250 divided by 84.9. Okay, what's that value? 1.415. Okay, so if we square that now, do some brackets here. Square it. Actually doesn't work. Never mind. So you can't use parentheses and brackets in the calculator. Same ones. Okay. Okay, so we were kind of off. So it should be 2.002225, but that's okay. It's because we rounded. So we probably won't want to round like that. We want to keep extra digits. So that's just a fair warning there. If we don't do that, we will get a very bad number. So if we do 2.002225, so this should have been, oops, sorry. So we should have got 2.002225. So I would so in this case I would underline the third significant figure so I know where to round in my final answer. Okay? So if we do that math again, we would get 32.00 divided by 2.002225. Oh, okay, so it doesn't really matter. It's still 15. Oh, okay, so it would round to actually 15.98, which would round to 16 for three significant figures. But let's just go over our calculation. 32 divided by 2.012. Okay. So yeah, so it does make a difference here. Our answer would be 15.9, but in the calculated answer, since the number is smaller than 2.012, it'll actually be 15.98, and we will round that to 16. So that is in fact methane gas. Okay. All right, so that's that problem. So the gas chapter, there's a lot of new calculations. So let's make sure that we are on top of things here. And then the next homework assignment will probably cover gases. So I will. It's important that we kind of talk about how to we talk about all these type of calculations because there'll be many, and on the next exam you might be asked about any one of them. Okay, so in the next video we will pick up with the derivations from ideal gas law behavior, and I think at the end of this lecture here we will actually be done with chapter 5. So that'll be gases. Okay, so I'll see everyone next time.